Hey there, curious minds, and welcome to the deep dive. Today, we're taking you on an incredible journey right into the heart of network routing. Imagine the most complex, really efficient traffic control system you can think of, but instead of cars, it's directing your data packets. Making sure every email, every stream, every single click gets exactly where it needs to go reliably and, well, super fast. That's the unsung hero we're exploring today, OSPFv2. We've compiled some truly fascinating insights. Our main source is this really in-depth OSPF v2 guide, and our mission really is to distill the most critical knowledge for you. So whether you're a networking enthusiast trying to connect the dots, or maybe just someone incredibly curious about the hidden intelligence powering our digital world, you're about to uncover some genuine aha moments.
Indeed. OSPFv2, or Open Shortest Path First Version 2, it's not just another protocol. It's really a foundational pillar of modern networking. It's the meticulous architect making sure your data travels the fastest, most resilient path across the network, often operating kind of seamlessly in the background of your digital life. We'll be breaking down its core concepts, introducing you to the specialized roles its routers play, and uncovering some of the clever features that keep our vast, interconnected world not just running, but actually thriving.
Okay, then let's unpack this deep dive into OSPF v2 and discover how it masterfully steers all our digital traffic. So, to kick things off, what's the fundamental idea behind OSPF v2? At its heart, our guide describes it as a link state routing protocol. Okay. And it uses these link state advertisements, LSAs, to build an identical area topology database among neighboring routers. That sounds like every router gets its own complete, totally up to the minute map of the entire network. Is that right? What's the big deal about having that kind of detailed map?
Well, that link state aspect you just highlighted, that's really revolutionary. It's a fundamental departure from older ways of routing. Think of it like this. A lot of older protocols, they only know the very next street corner a data packet needs to turn onto.
Right.
A very limited local view. OSPF-v2, though, it builds a comprehensive, identical blueprint, a full topological database in the entire network right inside each router. So it's not just about the next hop. It's about understanding every possible road, every intersection, maybe every shortcut. And this complete view, well, it allows OSPF-v2 to make incredibly intelligent, globally optimized path calculations, which leads to far more robust and efficient networks. But imagine trying to map every single street, every building, every alleyway in an entire country all at once. It'd be overwhelming, wouldn't it? So to manage this immense complexity, especially in really large-scale deployments, OSPFv2 very wisely structures networks hierarchically. It starts with what's called an autonomous system, or AS. That's essentially a large unified collection of networks operating under common administration. And then within this big system, it's further divided into multiple areas, each representing a more localized group of interconnected networks.
Okay, so if an autonomous system is like a huge national road network, then the areas are like distinct states, or maybe major cities within it. Each city manages its own local traffic, but they all connect back to the national highway system. That does help visualize how it keeps things organized.
Precisely. Yeah, that's a great analogy. Our sources show this hierarchical design really well, like in Figure 22. You can picture the network like a wheel. You have a central area 0.0.0, which is the critical backbone, the hub connecting everything. And then you have other distinct areas, say area 10.1 and 0.0.0 and area 10.2.0.0 kind of radiating out from it like spokes. This intelligent division into areas is absolutely crucial for scalability. It dramatically limits the amount of routing information and updates that need to be exchanged within any single area, which prevents information overload and makes even truly vast networks manageable.
So for you, the listener, just trying to stream your favorite show or hop on a video call, what does this foundational structure actually mean? It's really the unsung hero that lets your data navigate these immense global networks quickly and reliably. It enables everything from your lightning-fast web searches to those crystal-clear video calls that make sure the digital highway is always efficient, open, and rarely congested.
Okay.
Here's where it gets really interesting, I think. If OSPFv2 networks are these highly organized digital cities, there must be specialized roles for the routers within them, right? Like different jobs. Our sources highlight three crucial types, each with really distinct responsibilities that keep everything flowing smoothly.
Absolutely. These specialized roles aren't just about structure. They are absolutely critical for OSPFv2's overall efficiency, its resilience, and its ability to scale. They prevent any single point from becoming, bottleneck or causing a cascade failure. So first we have the area border routers, or ABRs. Think of these as the essential bridges or maybe gateways between the different areas in that central backbone. Area 0. An ABR is a very busy router. It actually maintains separate topological databases for each area it's connected to. So it understands the layout of, say, Area 10 and the layout of Area 20 in the backbone. And its job is to facilitate the intelligent exchange of summary routing information between them. They ensure that localized changes or maybe a burst of updates within one area don't just flood out and overwhelm routers in another area.
Right, keeping things contained.
Yeah.
Makes sense.
Then you've got the Autonomous System Boundary Routers, or ASBRs. These are the true gatekeepers or maybe translators of the OSPFv2 world. An ASBR connects an OSPFv2 network to external networks that are running entirely different routing protocols, maybe something like BGP, which runs the internet itself, or perhaps RIP for a smaller, older system. Their vital role is to act as interpreters, redistributing routes from these external protocols into OSPFv2 and vice versa, making sure there's seamless communication across these different routing domains.
Interpreters, I like that. Bridging different languages almost.
Exactly. And finally, especially on broadcast networks, think your typical Ethernet LAN, where lots of devices share the same wire. Effectively, we find designated routers, DRs, and backup designated routers, BDRs. Imagine a big meeting where everyone tries to talk to everyone else all at once. It's just chaos, right? In a network, this is called chatter. Too many routers exchanging information directly, creating lots of unnecessary traffic. To minimize this, OSPFv2 elects a DR on that segment. The DR becomes the central point for sending and receiving routing updates for that specific network segment. This dramatically reduces the number of connections needed. And the BDR, it's always ready, just waiting to take over immediately if the DR happens to fail, ensuring continuous operation. There's an election process based on router priority and then router ID to decide who gets these critical jobs. Figure 23 in the source illustrates this.
Wow, okay. So it's a meticulously organized system then. Each router type has a very specific, optimized job, from handling internal navigation between areas to connecting with the outside world and even managing local traffic to prevent bottlenecks. It really is like having specialized police, border control, and dispatchers all working together perfectly. What's the biggest design challenge these specific roles actually overcome?
I'd say the biggest challenge is complexity at scale. Without these distinct roles, every single router would potentially need to know about every other router, exchanging enormous amounts of data. It just wouldn't scale. These specialized roles, they segment the problem, they contain the information flow where it needs to be contained, and they provide crucial redundancy. This is what allows OSPFv2 to scale effectively, from small office networks all the way up to massive enterprise and service provider infrastructures without collapsing under its own weight.
Okay, that makes a lot of sense. But given the sheer volume of data and connections in modern networks, how does OSPFv2 stop itself from getting overwhelmed? How does it prevent information overload? It feels like there must be some incredibly clever built-in optimization strategies to ensure the network runs lean and mean.
Oh, absolutely. Preventing information overload and ensuring efficient operation is really central to OSPFv2's whole design philosophy. It's not just about connectivity, it's about efficient connectivity. One major technique for this is something called area range, which allows for route summarization. So instead of an ABR needing to advertise every single tiny little route within its area to the rest of the network, you can consolidate them. It takes a group of contiguous routes, networks that sit next to each other logically, and advertises them as a single larger address range, like summarizing a whole neighborhood with one zip code. This significantly reduces the number of those link state advertisements, the LSAs, that have to flow through the network, which shrinks routing tables and makes path calculations much faster.
Less information flying around, basically. Smarter, not harder.
Exactly. Then we have these area types, which are essentially like design levers. They allow network architects to surgically control what information flows where, tailoring an area's behavior to its specific needs and role. So you have stub areas. These are designed for maximum efficiency. They simply don't accept external routes, specifically those Type 5 LSAs we mentioned, the ones advertising route from outside the OSPF domain. This drastically reduces the size of their routing database. How do they reach the outside world then? Well, any traffic needing to leave the stub area for an external destination is just directed via a single default route injected by the ABR. Super simple routing decisions within that area.
Okay, so stub areas are like, I don't need the details of the outside world, just tell me how to get out if I need to.
Precisely. Then you have totally stubby areas, TSA. These take that concept even further. They're even more restrictive. They don't accept any external routes, Type 5 LSAs, and they don't accept summary LSAs, Type 3 LSAs, which carry those summarized inter-area routes from other areas. The only way out for any traffic from a totally stubby area is through that default route provided by its ABR. That's it. This makes them incredibly efficient and really simple to manage, often configured with just a simple no summary command on the ABR.
Wow, really locked down, minimal information needed.
Right. And then there's the clever hybrid, the not-so-stubby area, NSSA. This one's pretty neat. A standard stub area, remember, normally can't import external routes. But an NSSA provides a crucial exception. It allows an ASBR, that external gateway router located within the NSSA itself, to introduce external routes into the OSPFv2 domain. But it does so using a special kind of LSA, a Type 7 LSA. You can think of a Type 7 as like a temporary tag for external routes that are coming into an NSSA. The NSSA's ABR then takes these Type 7 LSAs and translates them into standard Type 5 LSAs, which can then be flooded throughout the rest of the OSPFv2 domain, like Figure 25 shows. This unique mechanism gives you flexibility, letting external routes originate from within a generally stubby area without sacrificing too much of the stub area's efficiency benefits.
That is incredibly granular control. So you can really fine-tune how private and resource-light each area needs to be, depending on its function in the bigger network picture. It really is like having different levels of security clearance and information access for different departments in a company. But what about dealing with genuinely redundant information? Networks can be messy, right? Maybe two routers learn the same external route.
Yeah, that definitely happens. And that brings us to another key optimization, the reduction of equivalent AS external LSAs. It's a pretty common scenario where you might have multiple ASBRs, maybe for redundancy, advertising the exact same external route into the OSPFv2 domain. Without a mechanism to handle this, the network could get flooded with duplicate information about that same destination, which wastes bandwidth and router processing power. So OSPFv2 uses an algorithm to identify and essentially eliminate these redundant advertisements. It ensures that only the best path, according to OSPF's metrics, for a given external route is actually advertised widely. It prevents unnecessary traffic and keeps the routing databases leaner. Figure 24 in the source gives a visual of this reduction. It's the network actively, trimming down redundant information to operate more efficiently. It's a proactive form of traffic management, not just passive forwarding.
What stands out to you as the most clever aspect of all these optimization strategies? For me, it's that OSPF isn't just about finding a path, but finding the best path, and doing so with the least amount of chatter and overhead possible.
I think you nailed it. For me, the cleverness really lies in its adaptability. These area types, the summarization, they aren't static rules, they are design tools. Network engineers wield these tools to sculpt the network's behavior, to shape how information flows. It means OSPF isn't a rigid one-size-fits-all solution. It's a highly tunable engine that can be optimized for specific traffic patterns, security requirements, and resource constraints. And that adaptability is absolutely critical for making it work effectively in the diverse and complex real-world networks we have today.
Okay, moving beyond the core structure and those really smart optimization techniques, OSPF v2 also has some advanced features. These seem designed for extreme flexibility and resilience. Let's talk about virtual links first. What exactly are they, and why would a network ever need something that sounds so abstract?
Yeah, virtual link does sound a bit abstract, doesn't it? But they are a very clever, though maybe somewhat specialized solution for those awkward moments in network design. They become necessary when you have an area border router, an ABR, that needs to connect to the backbone area at 0.0.0.0, always. But it doesn't have a direct physical link to any router in area 0, maybe due to geography or cabling limitations or just how the network grew over time. So instead of having to physically recamble everything, which could be hugely disruptive and expensive, OSPFv2 allows you to create a logical connection that's the virtual link. This logical link essentially tunnels or traverses through another non-backbone area, which we call a transit area. Our source has Figure 26 showing this. Imagine device B, and say transit area 1, needs to logically connect to device A in OSPF area 0, but its only physical connection is within area 1. A virtual link creates that invisible bridge between them, tunneling through area 1. It's a way to maintain the backbone's critical contiguous integrity and connectivity, even when the physical topology isn't perfectly aligned with the area 0 requirement.
That's amazing. It's like building a temporary invisible bridge or maybe a secret tunnel when the main road is out, or perhaps was never built directly in the first place. Sounds like a real lifesaver for maintaining that critical backbone structure without ripping everything up. And what about keeping the network running smoothly even during maintenance windows or unexpected outages? That's absolutely vital for businesses and users today. We see graceful restart and nonstop routing mentioned. These sound like the ultimate safety nets, don't they?
They really are. They are, quite literally, critical features for ensuring network stability and business continuity in modern networks. Let's take graceful restart, GR, first. GR allows an OSPFd2 router to restart its OSPF process. Maybe it's undergoing a planned software upgrade or a minor configuration change, or perhaps even recovering from an unexpected software crash without causing an immediate disruption in traffic forwarding. How? Well, the router can signal its neighbors, its adjacent routers, that it's restarting gracefully. Those neighbors will then basically hold on to the existing routing information they learned from the restarting router and continue to forward traffic along the last known good paths for a specific time, the grace period. This clever cooperation prevents what would otherwise be a noticeable network blip or outage. It makes planned maintenance virtually invisible to users and significantly mitigates the impact of unplanned software issues. It might even be enabled by default sometimes, the helper part at least.
So the network essentially keeps flowing based on the last known good map while the router sorts itself out.
Smart. Exactly. Now, nonstop routing, NSR takes resilience a significant step further. This feature is typically found on higher-end routing platforms that have built-in hardware redundancy, specifically redundant control plane modules, essentially, two brains for the router. With NSR, there's a primary control module actively running OSPF and managing the router, and a standby module that continuously synchronizes its state with the primary. In the event of a failure of that primary module, maybe a hardware fault, the standby module can immediately take over control almost instantaneously. The goal here is truly continuous operation with near zero interruption to the actual data forwarding. It often leverages and builds upon the capabilities of graceful restart to achieve this always-on level of reliability. This is absolutely essential for critical infrastructure, think financial trading networks, emergency services communications, things that absolutely cannot tolerate downtime.
Wow, so these advanced features are really all about resilience then. Keeping the network robust, adaptable, and crucially, online. Minimizing disruptions, whether planned or unplanned, and ensuring that the complex, interconnected world we all rely on just stays connected. They're like the backup generators and the redundant systems that keep vital infrastructure running smoothly, but specifically designed for our data networks. It's this continuous focus on uptime that we often just take for granted, isn't it? So when we pull it all together, what does this all really mean? From its intelligent hierarchical area divisions to its specialized router roles like ABRs and ASBRs, and then layering on these advanced features like smart route summarization, those not-so-stubby areas, the virtual links, and crucially graceful restarts and nonstop routing. OSPFv2 truly is a sophisticated master traffic controller for our networks.
It really is. It's an incredibly elegant and robust solution to that pervasive challenge of scaling and managing complex network topologies efficiently and reliably. OSPFv2 ensures that data finds its optimal path, minimizing congestion, reducing unnecessary information overhead, and maximizing overall network performance. It stands as a prime example, I think, of how layered intelligent protocols work together in concert behind the scenes. They create the remarkably seamless digital experience that, let's be honest, we often take for granted every single day.
Absolutely. This deep dive has really pulled back the curtain on the unseen architecture that underpins so much of our digital lives. Hopefully, you now have a clearer understanding of the meticulous planning, the sophisticated algorithms, and the layers of redundancy that keep our data flowing smoothly. From your simplest text message all the way up to the most complex global financial transactions. So next time you send an email or stream a video or just browse a website, maybe take a moment to consider this invisible, highly optimized network of protocols like OSPFv2 tirelessly working behind the scenes. How might understanding these intricate traffic rules and their incredible resilience change how you think about the internet's reliability? Or its incredible scale? And maybe even its future possibilities. Keep those questions churning in your mind, and we'll see you on the next deep dive.